The RPD training and guidance program displays its content through interactive 3D graphics visualization and animations. Where relevant, the program simulates real-life situations, like for example, setting the rig on location in areas with previous footprints. Furthermore, to become familiar with various control panels, the program uses unique interactive cross-referencing guides and simulations. On average, it will take about 10 hours to complete the training program. The exact time will depend on the user's knowledge level and comprehension. For example, when a user answers questions correctly, she will progress to the next topic. When a response is incorrect, the user will be directed to additional explanatory and remedial information. Consisting of the shown 7 lessons, the main training objective of the Rack Phase Difference (RPD) training and guidance program is to provide you with the following knowledge and skills. A. Thorough understanding of RPD's significance, its causes, effects, and limits. B. How to obtain and interpret accurate RPD measurements, both manually and by electronic system, and C. How to manage RPD to ensure safe operations and preserve the structural integrity of the legs throughout the various operational modes. The program is oriented primarily toward personnel, who are involved with the daily operations of jack-up rigs, rig movers, OIMs and barge engineers. Other users who will benefit from this training program include managers and engineers, representing the drilling contractors, energy operating companies, and the regulatory organizations. For the persons already experienced with RPD situations and countermeasures, the program will reinforce and extend their skills and knowledge base.
This training program covers the main causes and effects of Rack Phase Difference, RPD, including the related guidelines and management procedures for assuring safe and efficient operations. While this training program is applicable to all types of independent leg jackups, its main emphasis is on rigs with triangular legs and rack chocks. This first lesson introduces you to the general concept of Rack Phase Difference, RPD, its significance, and under what conditions RPD is likely to occur. During their service life, jackup rigs are used at various sites. Each such site represents a unique situation in terms of the operational objectives, environmental loads, water depths and air gaps, and seabed profiles and soil properties. Your rig structure is designed to withstand certain extreme loading conditions. Furthermore, the specific design includes a safety factor to take care of any unexpected loading as imposed by storm conditions or unaccounted interaction between soil and structure. For a structure to withstand all possible unexpected load scenarios, the resulting design would be too large and uneconomical. Additionally, the larger a structure becomes, the environmental loads it experiences also increase. Your knowledge and skill level have a significant contribution toward increasing the safety factor of your rig. Records of jackup accidents and failures from the past 20 years show that most of them occurred while setting up or coming off locations. As shown by the pie chart, the majority of problems were attributed to punch-through incidents. The second highest rate of accidents was attributed to an uneven seabed caused by a sloping floor, scour, and pre-existing footprints. Note, in many cases you can detect the potential for these accident scenarios by checking on the Rack Phase Difference, RPD. Rack Phase Difference, commonly referenced by the acronym RPD, is the measurable difference in the vertical position of the cords relative to one another within an individual leg. Shown is the standard cord designations for a triangular leg. On each leg, cord A is toward the bow, and cords B and C are toward the aft direction, respectively on the starboard and port sides. With respect to the shown reference plane, Currently, all three cords are at the same vertical position, and for illustration purposes, we will assume the rig is afloat. Therefore, for all practical purposes, stresses on the cords and their connecting members are equal and minimal. The vertical movement of cord A in relation to each of the other cords represents the rack phase difference. The RPD between cords A and B has changed the stresses on the connecting bracing members as follows. Braces number 1, number 2, and number 3 are now under tension, and brace number 4 is under compression. While similar stresses have resulted on the brace members connecting cords A and C, stresses on the brace members connecting cords B and C have stayed the same as prior to changing the vertical position of cord A. RPD occurs due to an uneven loading of the leg cords when the spud can is eccentrically supported, or when the spud can is subjected to a lateral, horizontal load. Shown is an enlarged view of the leg above and below sea level. In this configuration, the seabed is flat with no obstructions and perfectly leveled. In such situations, the downward force exerted by a portion of the rig weight and the resulting upward force of reaction from the seabed are aligned and equal. Accordingly, the cord heights are equal with no RPD. If you were to place the leg on a sloping seabed, the misalignment, eccentricity, between the downward and upward forces would cause variation in the cord heights. The higher the slope angle, the higher the cord height variation, and thereby, so is the RPD. Another major RPD cause is the misalignment between the centers of the leg well and the spud can. Such misalignment occurs when lowering the leg into a previous footprint where its center does not align with that of the spud can. As shown, prior to lowering the leg, the centers of spud can and leg well are aligned. Also known as splay, the resulting leg contour renders different cord heights, where in this case cords B and C are higher than cord A. Generally speaking, the major two causes of RPD are categorized under the types of interfaces between the seabed and the spud can, namely eccentricity and leg offset, splay. For further details regarding the specific situations under each category, refer to lesson number 2, Causes and Effects, Classifications. RPD is your friendly watchdog at your service, aimed to alert you against any possible leg damage. On a 3-legged jackup, damage to just one leg could result in catastrophic structural failure with consequential human losses and injuries as well. RPD is a reliable measure of the bending moment induced on the leg at the spud can seabed interface. The higher the bending moment, the higher is the RPD. At lower magnitudes, the bending moment is resisted solely by the stiffness of the leg structure. At higher magnitudes, the leg cords will make hard contacts with the lower and upper guides. As such, the resulting reaction forces will generate large loads on both the cords and the bracings. By design, the leg bracing are the weakest links. When the RPD gets to be too high, the braces are bound to fail under compression, buckling, or tension. The next in line will then be the cords. Lesson number 3, Global Mechanics, covers the details of leg-hull interface and the process by which the leg bending moment is resisted by the guides. If your rig is RPD prone, its operations manual must specify the allowable RPD limits. These limits should be based on accurate modeling of the leg structural members, cords, bracings, and spud can, and their interaction with both the guides and the seabed. To determine the RPD values, you will need to first measure the cord heights, also referred to in this training program as rack phase values, RPVs. The cord heights are measured and recorded for each cord on a leg. Whether it is a leg of 3 or 4 cords, the reading between 2 adjacent cords on an individual leg are subtracted to find the RPD values. The pair of cords with the largest differential is the one to be compared with the RPD limit specified for your rig. In lesson number 4, Limits and Measurements, you will cover in more details the specific RPD limits of your rig or rigs. Additionally, the lesson covers several techniques for measuring the RPVs and calculating the resulting RPDs. Simply put, RPD has the potential to occur with any leg type. However, some leg designs are more susceptible to RPD than others. Typically, this includes most legs which use rack chocks, as they have been designed with lighter braces, since most of the storm loading is intended to be supported through the cords. A leg design which does not use rack chocks is typically a stiffer design and is usually less susceptible to RPD, but there are trade-offs. The leg design more susceptible to RPD is generally lighter and experiences less loads from environmental forces, resulting in higher variable loads in both the afloat and elevated conditions. The type of jacking system aboard your rig plays a major role regarding the capabilities of RPD monitoring and the options of corrective countermeasures. Whereas most new rig designs provide for cords-independent control, majority of the older models are restricted to the simultaneous control. Basically, when considering individual cord control on older rig models, the brake releasing method might be the only practical option. For more detailed discussion about the two main jacking systems, SC and IC, and their related control panels, refer to lesson number 5, Jacking System and Control Panels. Additionally, you will find in this lesson very useful interactive cross-reference guides and simulations for the latest models of control panels. The most appropriate management method and procedure to minimize RPD will depend on the following main factors: soil properties and seabed profile, RPD growth trend throughout the jacking operations, and jacking control system. Prior to setting on location a rig prone to RPD, the main options for manipulating the seabed are stomping and reaming. Effectiveness of such options will depend on the soil properties. Aside from the seabed soil conditions and the operations stage, the appropriate management methods depend on the type of jacking system, SC or IC. The main management methods are as follows: reseating 0 RPD, changing the cord load via brake release and/or re-torque, reverse RPD, and hull tilting. For detailed coverage, refer to lesson number 6, Management Method and Procedures. The lesson concludes with a series of countermeasure procedures and how to measure their effectiveness, displayed by flowcharts similar to the one shown. Overall, after completing this lesson, you will gain the knowledge and skills necessary to decide which countermeasure is most appropriate and how to apply it safely and effectively. RPD phenomenon has been around for quite a while. In recent years, however, It has drawn more attention because of new innovations with rig's lighter structure and the progression into deeper, hostile waters with challenging seabed. Every situation involving RPD is somewhat unique. Furthermore, RPD management is not always a routine event. Lesson number 7, Assessment and Control, Practice, is a collection of various real-life cases involving RPD management. This is the lesson where you can apply your knowledge and skills to solving practical situations. This lesson covers the primary causes and effects of RPD, as instigated at the interface of the leg's spud can and the supporting seabed. As outlined by the shown flowchart, the most probable causes of RPD are categorized under eccentricity of the leg vertical reaction and leg offset, splay.
The topics covered throughout this lesson are eccentricity of leg vertical reaction, sloping floor, hard and soft soil, slope measurements practice, uneven seabed due to scouring practice review, leg offset, splay, previous footprints, definitions, punch through, rapid penetration, leg penetration curves, backflow, sliding effects while elevated and setting on location, and considerations of tidal currents and cycles.
This lesson consists of the following 2 main parts. 1. The differences in leg hull interface, rack chock versus pinion-supported rigs. And 2. The leg hull interface during phases of setting up RPD-prone rigs on location.
The topics covered throughout this lesson are environmental forces and moments, leg hull load transfer by guides, leg hull load transfer by rack chocks, guides versus rack chocks, comparison, leg design in RPD, induction type pinion motors, leg hull interaction under eccentric load, leg hull interaction under leg splay, and rapid penetration and leaning structure.
This lesson introduces the assumptions made to establish RPD limits for rig designs that are subject to RPD failures. The core of this lesson covers guidance regarding methods and gauges for RPD measurements and their meaningful interpretation.
The topics covered throughout this lesson are analysis background for RPD limits, environmental loading and soil foundation modeling, jacking operations model, storm survival model, general overall results, RPD effect on elevated mode, RPD limits for specific rig class, name, measurements of RPD, automatic and manual, rack gauges, RPD measurements procedures, Method 1 and 2. RPD measurements practice. Leg attitude visual observations. Leg attitude visual observations. Practice. Measurements of leg inclination by spud can direction. Legs inclination comparison. Tips for measuring RPD. And measurement stages.
The fifth lesson covers common jacking systems and their related control panels. The lesson starts with identifying the different jacking systems, and then proceeds with detailed coverage of various control panels, both central and local. After completing this lesson, you will gain essential knowledge regarding the capabilities of the various jacking systems. Additionally, you will become thoroughly familiar with the operations of your selected control panels.
The topics covered throughout lesson number 5 are jacking system types, SC and IC. Simultaneous cord, SC, jacking system. SC jacking system, control panel. SC jacking system, brakes release. Independent cord, IC, jacking system. IC jacking system, familiarization. IC jacking system, RPD readings. Pinion load monitoring systems, PLMS. Enhanced monitoring system, EMS. EMS, manual versus electronic RPD readings. And the re-torque function, familiarization.
This lesson covers management methods for assessing RPD situations and deciding on the most effective countermeasures.
The topics covered throughout lesson number 6 are RPD management, general. Dynamic trends of RPD growth. Spud-can soil interaction, hard versus soft soils. Seabed manipulation, pre-forming. Management for previous footprints. Scouring management. Reseeding, 0 RPD. Changing the cord load by brake release, SC and IC. Brake releasing guidance, afloat versus elevated. Changing the cord load, IC. Reverse RPD, IC. Hull tilting, soft to firm versus hard soil conditions. Removal of RPD while afloat, SC, versus IC. Removing RPD while setting up, elevating on location. Method A. Leg is extracted clear off the seabed. Method B. Leg is partially extracted from the seabed. And other management procedures.
You have covered a lot of territory, both theoretical and practical, throughout the previous lessons. By now, you should have a firm grasp on what is RPD, its causes and effects, how to measure it accurately, and the available countermeasures. In this last lesson, you will have the opportunity to apply the knowledge you have gained throughout the previous lessons. The lesson consists of actual, real-life situations as related to all aspects of managing RPD.
The topics covered throughout this last lesson are: Take 1, preliminary checklist. Take 2, manual measurements. Take 3, communicating manual measurements. Take 4, calibrations, manual versus electronic. And Take 5, leg pinning detection.
The RPD Training and Guidance program from Interactive Training Solutions is an excellent tool to have at my disposal, and it is the first RPD training program that I have seen, covering the subject of RPD thoroughly. I have used the program to my benefit. It is a program that I retain for continual use and not just as something that I can say I have completed as a one-off course. The program has allowed me to interpret what the soil conditions are communicating to the rig via RPD, and I have then been able to decide what action to take that has allowed me to elevate the rig to final air gap, without the RPD values climbing out of control. In my opinion, the RPD Training and Guidance program from Interactive Training Solutions is simply the best RPD training tool available to our industry.